So welcome everyone. It's a tremendous pleasure to have a friend and colleague, Christine DeTournay, as our speaker this morning. And Christine started working as a consultant for Itasca in 1986, and now she is a principal engineer at that corporation. She holds a geoengineering degree from the University of Liège in Belgium and a Master of Science and a PhD in civil engineering from the University of Minnesota. And as we know, her expertise is in the development of numerical models with application to coupled fluid thermomechanical problems. And in that respect, she has contributed to the development of multiple Itasca codes, and that includes FLAC 3D, 3DEC, and more recently Excite. And she is the principal developer for the groundwater flow and thermal logic in FLAC 3D, and has been involved in the implementation of constitutive models that are available within Itasca's continuum codes. And Christine, in addition to this, she has worked in consulting and development in various projects related to oil and gas, and this included work on hydraulic fracturing, as well as projects pertaining to underground waste repositories, geothermal applications, slope stability, soil liquefaction, CO2 sequestration. As you can see, Christine has a very diverse and comprehensive career, including more than 65 publications, some book chapters, and et cetera, et cetera. And so really a tremendous pleasure to introduce Christine DeTournay.
Thank you very much. Thank you for inviting me, John. It's really a great honor. And thank you to you, gang, for facilitating this. So today, I would like to walk you to a series of numerical simulation examples that we have used over the past 10 years almost to study, explore the topic of hydraulic fracture interference. And of course, I would like to acknowledge, the contribution of my colleague, Branko Damjanac, Murillo, who I think is here today, and Peter Kandalu is also here, I think. So here is the program of the tour. First, I'll show you a short overview of the numerical code. So I would like to tell you that this is not a presentation about the code itself, but since it is a little bit different from what is typically used in the industry, I would like to present it here. And then we'll tour the numerical simulation example that we have selected because they offer some surprising results, at least to us. So as you will see, some of the examples are pretty old. A lot of research has been done on the topic over the years, and especially more recently. So, though some of the points are not so surprising anymore, but they were at the time when we looked at it. So, oops, sorry. I would like to move this. Oh, sorry. So the first example is hydraulic fracture propagating in the close neighborhood of a pre-existing joint. And what was our expectation for the simulation? That there would be arrestor crossing. Next, we will move to another example that is a little bit more complex. It's the sequential creation of two hydraulic fractures. And since it is sequential, there was pore pressure dissipation involved between the creation of those different fractures, we were expecting a planar evolution. The third example involved injection in a borehole containing clusters. So the code that we are using to do the numerical simulation has a borehole logic. And there we were expecting to have simultaneous growth through those clusters. The fourth example involved hydraulic fracture created by borehole injection, but in a fracture layer. And there we were expecting extended diversion in the fracture formation. We'll see what happened because it's overlaid by a reservoir that is not as fractured as this one, I should say. And in the fifth example, we will just look at the result of a 2-well zipper stage treatment. So here is our overview of the code that we use. Is the 3D code that is developed by the company I work for, Itasca Consulting. And the code is called Excite. It's used to simulate propagation of hydraulic fracture in conventional, but also in naturally fractured reservoir. And it can model injection production for multiple borehole and multiple cluster. You see, there is like a picture on the left of the screen that illustrates the borehole with a series of clusters. The user can also use pre-existing joints which are derived from user-specified discrete fracture network. An example of that network is shown on the picture to the right of the screen. And in that code, hydraulic fracture propagation is modeled as intact rock failure in tension, but also as slip and opening on joints. The code is special because it uses a 3D lattice representation of the reservoir. The representation involves a quasi-random assembly of point mass which are connected by springs. There is a very crude representation of this lattice in 2D on the right of the screen. Those springs can break and form thereby, in the terminology of the code, they form microcrack. Now, a macroscopic fracture in that framework consists of chains of spring breakage. We use a small strain assumption, and for fracture flow, we use this network, a network of reservoir and pipe. The reservoirs are fluid nodes that are located at the location where a spring breaks, either at that location or at the location where the spring is cut by the pre-existing joint plane. And the fluid node is connected, one particular fluid node is connected by pipe to all the fluid nodes within a certain distance, which is of the order of magnitude of the lattice resolution. And as the simulation evolves and springs are broken, nodes are created, and pipes are installed, this system is evolving continuously as fracture grows. The code is fully coupled. The fracture conductivity depends on aperture, which is itself depends on the deformation of the mechanical model. The fluid pressure affects the deformation and the strength of the solid model. And we have also the coupling whereby deformation of the solid model affects the fluid pressure. So let's move on to our example of numerical simulation. But before that, I'd like to give a little preamble, just as to point out, as all of you know, I'm sure, that hydraulic fracture, they do follow the principle of minimal energy. This means that when they propagate in virgin rock, they tend to propagate in the direction normal to the local minimal stress, where it's easier to open up, right? And in fracture media, they tend to pick the easiest path, which can be either the most adaptly oriented pre-existing fracture and the virgin rock. And the topic of the tour is hydraulic fracture interference. And in most of the interference case that we observe, stress shadow is often, the main factor in influencing this interference. And we give here a very simple, uh, example, which is an axisymmetric crack, which is under uniform pressure, internal pressure. And we want to point out that, there are various things that happen in a test like this, because when you look at the vertical stress, of course, you have the expected tension that occurs, at the tip of this axisymmetric penny-shaped crack, but you also have a zone of compression that develop in the rock in the neighborhood of the lips of the crack. And it is this augmented compressive stress, which is caused by the fluid pressure in the fracture or by a residual fracture aperture when the fracture closed, that modifies the virgin stress state and then impact the direction of the principal stress, but also, of course, the direction and the amount of new and simultaneous growth of the fracture, the hydraulic fracture. So let's move to the example. And the first one that we would like you to, that I would like to present to you is the example of an hydraulic fracture formation through injection in the vicinity of a pre-existing crack. The pre-existing crack is a penny-shaped crack represented in brown here on the, represented in brown on the figure, to the left on the figure. Let me see if my pointer, yes, it does work. So here is the penny-shaped pre-existing crack. And, in 2D, what would we expect? We would expect maybe the hydraulic fracture to grow as a penny shape, then maybe, be arrested by this existing joint or cross it. And what we observed in the simulation was a little bit different. So here is our penny shape growing, interfering our hydraulic fracture, interfering with this pre-existing joint, but then it propagates, around the pre-existing crack. And at the end of the simulation, it's almost penny shaped, as if, it had forgotten about the existence even of that pre-existing crack on its path. So this is one result that we found, quite interesting, a 3D result typically, right? The second example is that of attraction and repulsion of two sequential hydraulic fracture. And this example is presented in the context of cave mining operation that often use preconditioning of the rock mass by hydraulic fracturing to increase the caving efficiency. In this technique, there is an array of hydraulic fracture that are generated from vertical borehole. And extensive field and lab observation have shown that closely spaced fractures, in fact, do not remain planar. In the numerical simulation, we will consider an elastic impermeable rock mass, we'll inject water. The stress state will be such that the minimum compressive stress is along the borehole axis, but we'll have an isotropic stress state in the horizontal plane. We will model sequential propagation of two hydraulic fracture. First, a deeper fracture will be followed by numerical simulation of shut-in and fluid pressure dissipation. At the end of this process, there will be lock-in stresses due to incomplete fracture closure. Then we will generate the second fracture and we'll vary the distance between the injection points. We'll consider three different spacing, and this is the shorter spacing that we utilize in this particular simulation. And what we observe is that the first fracture is a penny-shaped fracture represented in green on those plots. The second fracture in this simulation curved towards the first. But not only that, this is a view now normal to the plane of this particular plot. And what do we see is that the fracture, in fact, has a semi-cylindrical shape. So here we zoom in the direction normal to this plane, and we see this elongated fracture in that direction. So if we were looking at the footprint of this blue fracture, we would see an ellipse with, of course, a long axis oriented in the maximum in situ stress. When the spacing was enlarged in the simulation, we observe that the first one, of course, is still a penny shape, but the second one imitates the first. So it's also a penny shape, and there is still a slight dip towards the first fracture, but overall, the interaction is much weaker than when the distance between the cluster was smaller. When we increase the distance even more, we observe that the second fracture goes away, from the first. And still, if we look in the direction perpendicular to this particular plane, we see a semi-cylindrical shape. So those simulation results were, quite surprising, eye-opening for us. To understand the mechanism underneath, we use an axisymmetric equilibrium analysis, a very simple analysis. We use the continuum flat. There is no fracture evolution. Here we consider, a line of symmetry for the simulation. So only one lip of the first crack is represented. And we pressurize those two cracks. For the second one, we use different lengths and we plot the result that we obtain. So the summary of this simulation is given in this plot where we represent the angle of the major principal stress at the tip of the second crack. And this angle is, positive in the anti-clockwise direction, meaning that a negative value would correspond to the potential of the second fracture to be attracted by the first, whereas, this is, whereas, a positive angle would point to a repulsion behavior. So what we observe on the plot for small distance, relatively small distance between those two pressurized pre-existing crack, we see that a tendency for attraction that decreases as the distance increase. And then we move to repulsion tendency when the distance is larger, and when the distance, reach very large value, the second crack just ignore the first one. It's way out of its influence, and it tends to propagate parallel to the first one. So the findings from this numerical simulation, we are summarized on this slide. We have been using data from CADIA-E's preconditional trial test, and we observe attractive repulsive behavior between the two fractures depending on the spacing, but we also, observe a three-dimensional effect, which is the curving in the direction of the intermediate stress, which could potentially explain the elliptical hydraulic fracturing footprint that were observed at the site. Of course, those are, simulation that needs to be confirmed, by either lab or field experiment, but we still can use the code to explore what potentially could happen in situations like that. And this points, of course, to the importance of considering fracture interaction in the design of optimum spacing for preconditioning. The next example, consider the interaction of hydraulic fracture generated from borehole injection. And the framework, the context for this analysis is hydraulic fracturing in oil gas shale. The numerical simulation takes into account the two-layer model, whereby the bottom layer lays below the horizontal borehole in the simulation and is acting as a stress barrier, meaning that the minimum principal stress is much larger in the bottom layer than in the top one. And we will consider injection through the borehole using in one cluster 2, 3, and increase the number to 6 in this particular simulation. So those are the results that we obtain for in this two-layer medium for injection in just one cluster. So we see that I'm so sorry. We see that the hydraulic fracture first evolves as a penny shape, then it hits the stress barrier. Of course, its growth is impeded there as expected. So it's another form of interference, but a bit different from the one we have seen before. And the fracture, is growing like this.
Be good today, okay? Not
It
sure.
remains
a
semi-planar. If we consider two clusters, what happens? Those particular clusters are distanced by 30 meters. And what do we see? That those two fractures evolve simultaneously and have, parallel to each other. They have the same shape, but also the same size. For three clusters, first, to study the case of three clusters, first we turn back to the two cluster case and move those clusters closer apart. There, we still see that the two fractures have more or less the same size, the same shape, and move only slightly apart, because of the stress shadow effect. When we add a third cluster in the simulation, 50 meters apart, what do we see? We see that the middle fracture experience a growth repression. And this, is a result of a combination of stress shadow effect, but also slight inhomogeneity in the system that, creates a little bit of a delay. So the middle fracture is probably starting, a bit, later than the other, and its growth is repressed. So, we have seen what, in a simple example, what the stress shadow implies as far as modifying the stresses. So if we move now, if we move and add more cluster, we see one interesting fact, that the edge fracture, meaning the fracture at the edge of the strings of cluster, are promoted. But, the middle fracture suffer a growth impediment, and this is shown in this plot. We'll consider the case of 6 cluster, because here we again, observe that the edge fracture, which only have a one-sided stress shadow exposure, let's say, their growth is favored, but the middle fracture in this simulation experience directional growth. So the stress shadow effect, impact the growth of those middle fractures significantly in this simulation. For the fourth example, we will look at the interference caused by a fracture network on the course of hydraulic fracture. The context is, again, hydraulic fracturing in oil, gas, shale, and we'll take the example of the Appalachian Basin. The numerical simulation involves an excite model that contains 4 layers. So there is a target layer, which is the reservoir layer where the borehole is located. It's represented in green on this picture. And this layer is overlaid by a thicker layer, which is the main part of the reservoir. We do a preliminary analysis where we do not take into account any fracture network. So the whole reservoir consisting of the 2 layers is homogeneous, apart from some difference in properties. And we inject in 4 clusters. And what we observe is that the hydraulic fracture will grow first as penny shell in the target reservoir layer, and then they will, grow and hit the top of the reservoir and then grow laterally as decay and fracture. And what we plot here, the color plots, are contour of fracture aperture. So you see that the aperture tend to be larger in location where the stress shadow effect is less. View in a depth, side view, we see that 4 major fractures have emerged out of the 4 clusters. So one cluster is not active in this simulation due to the stress shadow effect. And one of the major fractures is going a little bit apart from the other, but we'll see a strong stress shadow effect whereby, those fractures grow laterally from each other, right? But they remain planar and they evolve in the direction of the perpendicular to the minimum principal stress. So this is just a preview. Now what we will do, we will add some fracturing in the target layer. And we represent the fracturing by a DFN with 3 families of pre-existing fracture. When this DFN is introduced in the target, only in the target layer in the simulation, this is what we observe. So this is a view of the fracturing that develops only in the target layer, and this is a view of the fracture that develop in the main part of the reservoir. And in both cases, we see that there is a tendency for the generated fracture here to go in the direction of the minimum principal stress. And we observe that, there is growth of, we can say 3 major main fracture, both in the target, both in the target layer and in the reservoir above it. Of course, the main effect here compared to the previous one is linked to the dimension of the fracture, which is much less in the reservoir here than in the previous example due to the diversion, that is experienced by the fracture in the DFN. So we see other view of the result here. We see a map view of what happens in the fracture layer, and we see a map view of what is happening in the retica. In the depth view, here we show both layers, but here we show only what is happening in the main reservoir. And one aspect of the simulation that surprised us was that the main fracture, there is a breakdown in the main reservoir that starts as a swarm of smaller fracture from which only 3 major ones emerge, hit the top of the reservoir. And of course the emergence point of the major fracture, they do not correspond to the location of the cluster below it due to the diversion experience, in the fracture layer below it. So we saw that those results were quite interesting. If we have to summarize them, we saw in that particular simulation involving the DFN, simultaneous generation of major fracture in not only in the fracture, but also in the uniform layer above it. And those fractures were quasi-planar and normal to the minimum principal stress as expected. The fracture breakout in the uniform reservoir started as a swarm, and from which major fracture emerged. And their location of the major fracture was off-centered compared to the cluster. The similarity in overall fracture pattern in the two layers is attributed to the rather high strength of the pre-existing fracture and also the relatively small thickness of the fracture compared to the uniform layer. The final case that I will walk you through is a simulation of hydraulic fracture interference in a two-well zipper treatment. It's again a four-layer model. The layers are intact. There is no fracture network involved in the simulation. We have two wells, each with 3 stages of 4 clusters. And the fluid in this simulation is loaded with propane. And we use a zipper type treatment whereby we inject from one cluster in one of the wells. Then we follow this by numerical simulation of pressure dissipation, move to the next well for the second stage, and repeat this process, injection, dissipation, and go back and forth between the two wells. And the results of those simulations are represented in plain view. So all of those fractures that we see the trace of on those plots are PKN type of fracture that, like evolve to the top of the reservoir. And we see, in the first stage that, fracture originate from all the 4 clusters in this stage. They interfere. There is, fracture interference between them. Then when we move to the second stage, we observe that, some of the fracture, they really take it easy. They don't only, propagate on their own, but they also utilize, the path that was, generated by the fracture from the other well. Moving to, the third stage, we see that, some of those fractures are pretty short compared to the previous case, but this is mainly due to the fact that they utilize pre-existing fracture to grow. This is what happened in the 3, 4 stage, 5th stage, and at the end, this is a picture of what we observe. So, it's maybe people expected, propagation of parallel fracture of more or less equal size, center at the borehole, but the end picture is indeed quite different, at least in this simulation. So here is a summary of the observational findings. We want to point out that in this particular presentation, we use the code as a tool to uncover some of the mechanisms that could take place in, a particular simulation. We concentrate, on a descriptive approach, of what could happen in those in the field, and all of those need, like the backup of either laboratory or field observation but the numerical code is used as a tool to uncover possibilities. So here is a summary of what we illustrated. So what we anticipated in the two fracture simulation was arrest or crossing, and instead we found that the hydraulic fracture decided to wrap around the pre-existing joint. In the second example of sequential injection, we expected planar evolution, but instead we observe attraction repulsion of the hydraulic fracture. So in a borehole injection, where we use multiple clusters, we were expecting simultaneous growth of the hydraulic fracture from those clusters, but instead we observe suppression and delay. And in the fracture layer injection, we expect a major diversion in the pre-existing DFN. And what we observed in addition to that was free breakout of fracture in the overlaid homogeneous layer. And in the 2-well zipper stage injection, frankly, we didn't know exactly what to expect. We expected a lot of numerical issue, but thanks to Murillo, none of that happened. And Franco, of course, we observed attraction, repulsion, suppression, delay, but also intrusion from new fracture in the existing one. So this is the end of the talk. So thank you for your attention. And if you have questions, I will try to respond to you.